When electrical power or pump flow disappears, the accumulator must do more than preserve pressure. It must deliver enough usable oil through the actual valve circuit to complete a defined safe movement under the worst credible load. A nominal shell capacity alone cannot prove that a suspended load will lower predictably. A clamp will release, a guard will close, or an actuator will retract from danger. Sizing begins by defining the safe state. Specify the initiating failure, required direction of movement, allowed delay, end position, movement time, and measurable acceptance criterion. Controlled shutdown and emergency stopping may impose different duties. Gravity may assist motion in one direction and oppose it in another, while friction should never be assumed to remain available as the safety mechanism. Valve behavior after power loss is equally important. Spring return solenoid valves may not create the required flow path, and pilot-operated valves may need minimum pressure to shift. Check valve orientation, counterbalance settings, isolation paths, and flow controls must be reviewed to confirm that stored energy remains connected to the intended actuator without discharging into another branch. Required oil volume starts with actuator geometry. Extension uses the full piston area, while retraction uses the annular area after subtracting the rod area. Multiply the correct active area by the emergency stroke. Rotary actuators and hydraulic motors require equivalent displacement for the necessary angular movement. Then account deliberately for hose expansion, fluid compressibility, internal leakage, valve overlap, and pressure losses. Margins should correspond to identified uncertainties. Combining a conservative load, low assumed efficiency, leakage allowance, and broad reserve can cover the same risk repeatedly. The result may be unnecessary stored energy, slower recharge, and higher cost. A documented boundary condition table makes each assumption visible and prevents hidden double counting. Usable delivery is governed by the pressure window. The upper state is the maximum approved charging pressure available during normal operation. The lower state is the minimum pressure at which the actuator can still finish the safe motion at the required speed. That minimum must include load force, active area, mechanical friction, return line back pressure, valve losses, and any counterbalance pressure that must be overcome. Gas precharge establishes the starting condition. If it is excessive, the accumulator may accept too little oil or reach the lower circuit pressure before enough fluid is delivered. If it is insufficient, bladder deformation and unstable operation may increase. Precharge must be defined at a reference temperature and checked with the fluid side safely depressurized. Using the selected manufacturer's method for the actual pressure window, discharge rate, elastomer, and duty. The gas calculation must also reflect discharge behavior. A slow process may approach isothermal conditions, while rapid emergency discharge is closer to adiabatic behavior. Temperature changes gas pressure, fluid viscosity, leakage, seal response, and pressure drop. A unit adjusted in a warm workshop may behave differently during cold startup, so credible temperature limits belong in both the calculation and the test plan. Component selection must cover more than accumulator capacity. Ratings, materials, ports, mounting, isolation devices, dump provisions, hoses, valves, and model-specific compliance evidence all require confirmation. Elastomer compatibility must address the actual fluid, additives, and temperature range. Company-level certificates or product family claims do not establish approval for a particular model. Validation must reproduce the real fault on the installed circuit. Test at adverse load, low temperature, minimum charging condition, and relevant valve states without bypassing protective controls. Record precharge at its reference temperature, charging pressure, pressure at the beginning and end of movement, actuator travel time, load condition, valve state, and fluid or ambient temperature. Maintenance procedures must treat the accumulator as a continuing source of hazardous energy after the pump stops. Isolation points, discharge verification, mechanical blocking where required, and authorized nitrogen service methods should be explicit. Periodic proof testing should reflect leakage, seal aging, precharge retention, machine use, and environmental exposure. Finally, change control protects the sizing basis. A replacement cylinder, altered counterbalance setting, longer hose, different fluid, revised sequence, or new operating temperature can change displacement, losses, timing, or material compatibility. Safe emergency return depends not on stored pressure alone, but on verified usable volume, a valid pressure window, correct valve behavior, and demonstrated completion of the required motion.